Very good morning, children. Today, class 12 children, today let us discuss about the lesson 14, the last lesson, semiconductor electronic devices. This is very important lesson. It's not like other lesson which is clubbed up for the weightage, but this lesson alone carries 7 marks. Whereas when you take dual nature of light or atom or nuclei, it has been clubbed up together and then given you some weightage. But Cbse has given a separate weightage for the semiconductor electronic devices, that is 7 marks. So from the first line till the last line, if your concepts are going to be clear, definitely you can get 7 out of 7. Now today in this class, I am going to teach you the entire concept with very easy way of understanding. So now, before getting into the chapter, let us recall in olden days, we were using for electronic devices, we are using for the charges to flow, we are using only vacuum tubes. But then it is very bulky and also require, cathode and anode, you have to give some external voltage. So it is not highly efficient. So therefore, we were able to find out the semiconductor material itself, it is used for controlling the amount of charges. Hence, we are going to learn about the basic of semiconductor and also higher efficiency compact. So all these are added criteria for making this used nowadays, and it has created a greater impact in the world, and you must be knowing about it. So now conductor. So when we talk about conductor, we all know that it conducts. So conductor conduct electricity, right? So conductor conduct electricity, and insulator does not conduct electricity. You must be knowing. But semiconductor, I think you must have heard, always saying that it will conduct only at certain temperature, or you can say certain condition. So therefore, you must have heard it partially conducts. So it is conducting only at special condition. Conducts only at special conditions. So now we have to know about what is the difference in conduction about conductor, semiconductor, insulator. Quickly, let me just give you a gist of it. We all know that nucleus, when you take, around the nucleus, shells are there and electrons will be revolving around the nucleus. So for example, here when I take for silicon or anything, any material when you take, so there are a lot of shells in that outermost electron. So this is outermost shell electron is called as valence electron, which is responsible for the conduction, which we know. But this is only one atom. So now each electron carries its own energy, therefore it has its own energy level. But at the same time, suppose instead of only one silicon atom or only one atom, I am taking generally an atom. If you take another atom, and then these electrons will be revolving around the nucleus, and there is a possibility for overlapping of these shells, due to which each and every electron has its unique value of the energy and forms a band called as energy band. So for example, if you take valence electron, so if you take for example, this is a valence electron which is present here. So this is valence electron, so this has got some energy, and the energy level create due to the valence electron, you call it as valence band. For example, in this shell you have, for example, let us take, so this shell has got unoccupied electrons, empty. For example, this shell has got 18 electrons to fill, but I have filled only 4 electrons. So the remaining is going to be an unoccupied, right? All this also carries energy. And if this valence electron has got its energy, the group of the energy levels, you call it as valence band. Valence band. So, continuous energy distribution, the adjacent, that is nothing but upper valence band energy levels, just one above the higher valence band energy levels, you call it as conduction band. This is conduction band. So, what do you mean by energy bands? Energy bands are nothing but energy levels. What energy levels? Continuous energy levels. Let us see in the NCERT textbook. Due to that, it forms a group. So, let us see that in NCERT here. Yeah. So, now this is according to Bohr atomic model, in an isolated atom, the energy of any of its electron is decided by the orbit in which it revolves. So, the energy of any of the electron decided by the orbit in which it revolves. But when atoms comes together to form a solid, they are close to each other. So, the outer orbits of the electron from neighboring atoms would come very close, or even it could overlap. So, therefore, when it is overlapping, this would make the nature of electron motion in a solid very different from that in isolated atom. So, that is why I have specified when it is overlapping, so it may carry different energy levels. So, therefore, you can say here the energy which includes the energy levels of the valence electron is called as valence band. So, the energy which includes the valence electron, you call it as valence band. Whereas, the energy which just above the valency band, you call it as conduction band. You can see here the energy band which includes energy levels of the valence electron is called valence band. The energy level above the valency band called conduction band. So, let us take it to the whiteboard. Yeah, so I am taking to the whiteboard. Yes. So, inside the crystal each electron has unique position, and since it has got a unique position and no two electrons see exactly the same pattern of the surrounding charges. Because of this, each electron will have a different energy level. So, therefore, these different energy levels with continuous energy variation are called as energy bands. I have already told you each and every electron. For example, when you take a nucleus plus Z, around the electrons will be revolving in a permitted orbit. So, now let us suppose this is the valence electron. So, therefore, it has its energy. Hence, the valence electron energy forms a band called as valence band. With no external energy, all the valence electron will reside in the valency band. So, the energy band which includes the energy levels of the valence electron is called as valence band. The energy band above the valency band is called as conduction band. I have already pointed out that only these valence electrons are present. If one atom, this is atom 1, if there is a chance to overlap with another atom, so what happens? The valence electron shells, that means the electron that is present in the valence shell may overlap, and therefore they acquire different energy values, hence it has energy levels. And also in this valence electron, it does not mean that the shells are fully occupied, there are unfilled energy states. So, that is nothing but the conduction band. So, what is conduction band? Just above the valency band, the energy levels form a group that is called as conduction band, and the energy level formed due to the valence electron is called as valence band. Hereafter, you will have to call this as valence band. Valence band, and conduction band is just above the valency band. So, So, that is almost empty over here. So, now if the gap between valence band and conduction band is very small, if the gap between the valency band and the conduction band, this is conduction band. What is this line which I am noticing, which you are noticing? That is all different energy levels. If the valency band and the conduction band exactly overlaps, so if it is overlapping, the valence shell electron is there, right, without having any external energy. Without having any external energy, the valence electron easily jump to the conduction band. Hence, conduction is possible. Conduction is possible. So, when does the conduction is possible? In conductor only conduction is possible. That means, in conductor, the valence band energy levels is overlapping with the conduction band. So, therefore, conduction is possible only if the electron jump to the higher level. So, jump to the conduction band. So, that is happening in the case of conductor. Why? Because both of them overlap. Which is overlapping? Valence band and conduction band is overlapping. But what is valency band? The energy band which includes the energy levels of the valence electron is called as valence band. The group of energy levels of the valence electron. The energy band just above the valency band is called as conduction band. With no external energy, all the valence electron will reside in the valency band itself. If the lowest level in the conduction band happen to be lower than the highest level of the valency band, so that means that is overlapping. If valency band and conduction band overlaps, the electron from the valency band can easily move into the conduction band. So, normally the conduction band is empty, but when it overlaps on the valency band, electrons can move freely into it. This is the case with the metallic conductors. Hope you understand, children, why the metallic conductors conduct nature. Is very easy to understand. Electrons in the valency band is easily moving to the conduction band as both valency band and conduction band are overlapping. This is conduction band, this is valence band, both overlapping. In valency band, what is there? That is valence electron energy level. Conduction band is empty. If they overlap, the electron easily jump and then conduction is possible. Okay, children, hope you understand. But in the case of insulator, something different. In the case of insulator, the valency band and the conduction band. In the case of insulator, the valence band in which what is there? Valence electrons, or the valence band and the conduction band both are separated by a vast energy gap. That energy gap is greater than 3 electron volt. So, therefore, the electrons from the valency band is unable to move towards the conduction band. Hence, you can say that it is empty. Is there any external agency you can provide so that the electrons can be jumped? No. Even if you provide external agency, there is no possibility, or you can say that very 0.0001% of the possibility for making the electron to jump to the conduction band. Hence, our studies is restricted to learn about the intermediate one, that is semiconductor. Why is it so? Because in the semiconductor, the valence band and the conduction band is separated by an energy gap of less than 3 electron volt. Then there is a possibility for the electron that is present in the valency band to move towards the conduction band with the help of external agency. So, hence we are going to learn detail about the semiconductor. How is the possibility for the electron in the valency band and make it to move towards the conduction band, and the conduction is possible. So, can we move to the next? So, basics I have told you about. Now, before going to the base, like entire part of the semiconductor, before going to the enhanced learning of the semiconductor, let us learn about the metals, the resistivity, that is very low resistivity, or you can say high conductivity. It is in the order of 10 power minus 2 to 10 power minus 8 ohm meter. Which one? Metals. The next one is semiconductors, that we will come back later after learning this insulator. You look at the insulator, it is very high resistivity, 10 power 11 to 10 power 19 ohm meter, hence that is very least conductivity. You can even say that negligible conductivity. But in the case of resistor, semiconductor, they have a resistivity or conductivity intermediate to metals and insulator, that is 10 power minus 5 to plus 6, 10 power 6 ohm meter. Hence, there is a chance for tuning this conductivity by means of some additional parameters. So, let us learn about the semiconductor, how to improvise the conductivity. So, now before learning semiconductor, so semiconductor, give an example of semiconductor. Semiconductor partially conducting, example is silicon. Example is silicon and germanium. These two are considered as semiconductor elementary material metals. So, elementary materials, silicon and germanium. Silicon valency is 4 and germanium also valency is 4. But then though valency is 4, the silicon, the valence electron that is present in the 3n state, the valence electron is present in the 3n state, whereas germanium, the valence electron is present in the 4n state, little far away from the nucleus. So, this is nucleus. So, 1, 2, 3, this is silicon. So, now 3n state, the valence electron is present, whereas in the case of germanium, 4n states, 1, 2, 3, 4. So, 4n state, the valence electron is present. So, energy required is far away from the nucleus for the germanium. So, therefore, energy required to remove, this is nothing but ionization energy. What energy, children? Ionization energy. What do you mean by ionization energy? Energy to remove the electron from the shell, because it is tightly bounded to the nucleus, right? So, what is the amount of energy required to remove this electron from the shell for germanium? For germanium, it is 0.75 electron volt, or you can simply say 0.7 electron volt. Whereas for the silicon, this ionization energy little higher, ionization energy is little higher, 1.1 electron volt. Even though little higher, this also can be used for making all electronic material. So, hence we are going to learn about both silicon as well as germanium. Okay, you may be wondering, what about tin? What about carbon? So, carbon, what about carbon? Carbon valency is also 4, right? And what about tin? That is also tin. So, that is also valency is 4. But here also valency is 4. But why don't we learn about this? Because tin is a metal, already it is conducting. Carbon, it is a insulator. How do you say carbon is an insulator? Because the valence shell is very closer to the nucleus. So, first shell 2 electrons, second shell 4 electron, it is bounded to the nucleus. Hence, it is very hard to remove this electron from, or ionization energy is very high. Since ionization energy is very high, so hence you can say that very high, hence energy to remove the electron is very high. So, therefore, it is considered to be an insulator. Hence, let us not learn about carbon, only we are going to learn about these two things, that is silicon as well as germanium. So, pure semiconductor, elementary semiconductor material is silicon and germanium, the valency is going to be 4. So, come let us learn about silicon and germanium, that is pure semiconductor. So, there are two types of semiconductor, children. Semiconductor is classified into two types. One is pure semiconductor. This pure semiconductor is technically called as, or professionally called as, intrinsic semiconductor. What semiconductor, children? Intrinsic semiconductor. So, the pure semiconductor is called as intrinsic semiconductor. This intrinsic semiconductor, pure silicon, example silicon, or you can say that germanium, pure semiconductor. What is the valency of silicon and germanium? 4. Okay. So, now let us discuss about pure semiconductor and then go to the next type semiconductor, that is nothing but doped semiconductor. Why do we need to learn about doped semiconductor? You will come to know now. Okay, let us first of all learn about pure semiconductor and come back there. This pure semiconductor I am dividing into 2, children. So, what are the 2? T is equal to 0 Kelvin, I am going to discuss about, and then another one I am going to discuss about T greater than 0 Kelvin. So, let us learn about T is equal to 0 Kelvin. T is equal to 0 Kelvin, let us take silicon, valency is 4, 1, 2, 3, 4, it forms covalent bond with the adjacent silicon atom, very tightly bonded to the neighboring silicon atom. Since it is very tightly bonded, there is no free electrons. When can you say conduction is possible? Only if there is any free electron, therefore energy to remove this is very easy. But here no free electrons. Since no free electron, therefore no conduction. No conduction at low temperature. At low temperature. So, there is no possibility for the conduction of semiconductor at low temperatures. Whereas, what about T greater than 0 Kelvin, that is high temperature, is nothing but room temperature. What is happening? T greater than 0 Kelvin, it forms covalent bond with adjacent silicon atom. It is forming a covalent bond, but then though it is forming a covalent bond with adjacent silicon atom, what happens, it is very interesting due to this is higher temperature. So, due to thermal agitation, thermal means heat, due to thermal agitation, number 1, covalent bond breaks. Covalent bond is broken. When the covalent bond is broken, what will happen? The electrons are left free. This electron left free. Electron is left free. Okay. The free electron which is left free is there, no? So, that will be loitering around. This will be loitering around as a free electron. Okay, let it loiter around. That is responsible for conduction. So, therefore, energy to remove this electron is very, very less. Easily you can energy to remove this electron. Energy to remove this electron, remove, is least, very less. But at the same time, very interesting phenomenon, just look into it. This has pair, this has pair, this has pair, this do not have pair because electrons are left out. So, the electron which is left out, what happens? What is created? A vacancy is created. What is created? Vacancy is created, vacancy. Electrons are left free, vacancy is created. What is that vacancy do? Vacancy is nothing but an empty space. That is nothing but an empty space. The empty space created, what does it do? It pull out the electron from the neighboring covalent bond, snatch out. One electron is already left free. So, this one electron is creating one hole, creating one vacancy. One vacancy is otherwise called as, it is style called as one hole. One vacancy is nothing but one hole. This one hole, what does it do? Try to snatch out the electron from the neighboring covalent bond. So, try to pull out this electron. So, the electrons are pulled out and then occupy the place. When the electrons are pulled out and occupy the place, apparently what will happen? This hole will come and occupy this position. Can you see the hole moment? Already the hole moment was in the first site. Now what happens? The hole has moved to site 2. So, apparently the hole is moving here. So therefore, the hole is also responsible for conduction. So therefore, a hole and an electron is responsible for conduction. Hole and electron. Electron hole is responsible for conduction. How do you say it is responsible for conduction? How do you say it is responsible for conduction? Because electron is knocked out, which you know, knocked out electron is producing a vacancy that is called hole. The hole apparently moves from one side to another, so electron hole is responsible for conduction. So therefore you can say number of electron per unit volume, that is number density, is equal to number of holes is created. Ne is equal to NH is created. So though Ne is equal to NH is created, you can say that Ne is called as number of intrinsic charge carriers, Ni, which is nothing but number of intrinsic charge carrier. Number means number density of intrinsic charge carriers. Charge carriers. So therefore you can say Ne is equal to NH is developed. Where Ne is equal to NH is developed in a pure semiconductor only at T is equal to greater than 0 Kelvin. When T is equal to 0 Kelvin, no free electrons, no conduction possible at low temperature. So hence you can say that now T is equal to 0 Kelvin, the conduction band is empty. Whereas the valency band alone will be filled with electrons, that is valence electron. But in the case of T greater than 0 Kelvin, due to thermal agitation, the electrons from the valency band, the electrons from the valency band can easily jump to the conduction band. So I can say that this is the electron, thermally generated one, 1, 2, 3, 4, all these are thermally generated one. So you can say thermally generated. Thermally generated electrons. If it is thermally generated electrons go over there, so what happens? The hole will sink down, because wherever the electron is moved up, in that place hole is created. So you can say that it is the hole is created over here. Okay, a hole is created here. So you can even see that the energy band diagram, so you will have a clarity of idea here. Okay. So now intrinsic semiconductor T greater than 0 Kelvin. So how many holes? 4 electrons went up. So therefore you can say that 4 holes are created over there. So same thing you have to draw it here. So in this case 4 electrons created. So therefore I have to draw 4 holes. So 4 holes I have showed. So this is all about intrinsic semiconductor. So now come back here. I was talking about intrinsic semiconductor, that is called as pure semiconductor. So T greater than 0 Kelvin conduction is possible, T is equal to 0 Kelvin no conduction is possible. But then the Ne is equal to NH is not enough. Since it is not enough, I wanted to just improvise the doping. So improvise the conduction, so therefore doping is necessary. What do you mean by doping? Doping, why do we need it? In order to increase the conductivity. So the doping is nothing but adding suitable impurities. Adding suitable impurities. Why do we need to add suitable impurities? In order to increase conductivity, that's it. To increase conductivity. To increase conductivity, therefore doping is done. So therefore this kind of semiconductor is called as doped semiconductor, or you can simply called as extrinsic semiconductor. What semiconductor? Extrinsic semiconductor. Extrinsic semiconductor. What is intrinsic semiconductor? That is pure semiconductor. Whereas extrinsic semiconductor is doped semiconductor. So what is doping, children? Adding suitable impurities to pure silicon atom or germanium atom. Adding suitable impurities to silicon or germanium in order to increase conductivity. The doped semiconductor is called extrinsic, which is divided into 2 types. One is called as positive type, that is p type. Another is called as negative type, that is nothing but n type. So all this we are going to see now. So now let us see the mechanism of pure semiconductor. Mechanism. So mechanism of pure semiconductor. So this mechanism of pure semiconductor I have already discussed about. T is equal to 0 Kelvin, no free electron, no conduction, and at low temperature there is no possibility. But high temperature, due to thermal agitation, electron is left free, and one electron which is left free produces one vacancy. What is that vacancy? Called as hole. So therefore T greater than 0 Kelvin, one electron, one hole is created for one silicon atom. Therefore n number of silicon atom, n electron, n hole is created. So you can see here the energy band position in a semiconductor at 0 Kelvin. The upper band called as conduction band consists of infinitely large number of closely spaced energy states. The lower band called the valence band consists of closely spaced completely filled energy states. It is fully filled, it is empty. So this is energy gap here. So silicon. So now in order to increase the doping, in order to increase the conductivity, doping is done. So before that I wanted you to see about this is valency band and conduction band when it is overlapping. So therefore it is called as conductor. Greater than 3 electron volt. So therefore it is called as insulator. Less than 3 electron volt, therefore it is called as semiconductor. So this is a general representation of valency band and conduction band. The valency band, this is conduction band. So hope you understand why it is given electron energies keep on increasing from valency band to the conduction band. So now let us go for explaining the stuff. Right, mechanism of extrinsic semiconductor. Extrinsic semiconductor. So you must know about doping. What type of dopants are needed? What type of dopants? Doping we are saying, but what type of dopants? Why do we choose that? Number one, there are two types of dopants. One is pentavalent impurity. Pentavalent impurity. Another one is trivalent impurity. Trivalent impurity. Pentavalent impurity, what is an example of pentavalent impurity, children? Pentavalent impurity is 5 rise. Valency is 5 no. So what and all is 5 valency element? Phosphorus, yeah, arsenic, antimony. Phosphorus, arsenic, antimony. Similarly, what is trivalent impurity? Example, aluminum, yeah, boron, indium. Iron, indium. Okay, let me write itself. So all these are trivalent impurity. Aluminum, boron, indium, iron. Now, why do we choose only pentavalent, trivalent impurity? You may be asking, right, why? Why not you choose any other impurity? Silicon is tetravalent, 4 valency, but why do we want to choose that? So now let us see. For selecting the impurities, characteristics of dopant. Characteristics of dopants. The dopants must have, that more dopant must have the size compatible to the size of silicon atom. You should not disturb the crystal structure. So you should size must be compatible to the size of silicon atom. Must be. The dopants must be compatible to the size of silicon atom, silicon or germanium atom. And number 2, it should not disturb the crystal structure. It should not disturb the crystal structure. As well, number 3, it should definitely increase electrical conductivity. It should increase the electrical conductivity. That is our ultimate aim, right? Increase the electrical conductivity. pure semiconductor at high temperature, equal number of electrons and holes are generated, so which can be removed by just, these electrons can be removed by giving very, very small amount of energy. But then here we are not having enough charge carriers for the conduction, hence to improvise the conductions we are going to go for the dopants, adding dopants. So increase electrical conductivity. So therefore the reason why we have chosen this pentavalent and trivalent impurity, because it is meeting the characteristic, meeting the criteria of the dopants. What are the three criteria, children? Yes, it should be compatible to the size of silicon atom, it should not disturb the crystal structure, it should exactly fit into the size of silicon atom, and of course it should increase the electrical conductivity. Hence two such impurities are used. Pentavalent impurity valency is 5 and here trivalent impurity valency is 3. So now let us take pentavalent impurity. Pentavalent impurity I am going to take adding pentavalent impurity. Adding pentavalent impurity. What is happening when you add pentavalent impurity? Very simple, children. Silicon valency is 4. I am taking phosphorus example. You can even take any other pentavalent impurity. Suitable impurities, phosphorus 1, 2, 3, 4 electron form a covalent bond with the adjacent silicon atom. Yeah? Yes, right? Now, whereas the fifth electron is there, right? For the phosphorus atom has 5 electrons. So it is left free. So energy to remove this electron is very, very simple. Very less. You can just snatch it out. But one phosphorus atom is donating 1 electron. Therefore it is called as donor impurity. Because it is donating 1 electron. So it donates 1 electron already due to silicon atom. Due to silicon atom, you have Ne is equal to NH exist. But on addition of impurities, you can't increase this number of electrons and hole that is present in silicon atom. As because you are adding impurity, that will give you some more electrons. So left free, 1 phosphorus atom produces 1 free electron. Here how many phosphorus atom we have taken, children? Here we have taken only 1 phosphorus atom. 1 phosphorus atom has got 5 electrons, so therefore 4 electron forming a covalent bond, whereas 5th electron is left free. So 1 electron is left free by the phosphorus atom, therefore 2 phosphorus atom, 2 electron, n phosphorus atom, n electrons. So hence you can say that on adding phosphorus atom, P atom to silicon, excess number of electrons are produced. So Ne is greater. So Ne greater than that of NH is produced. So therefore you can say this pentavalent impurity you are adding rich in electrons. Since it is rich in electrons, therefore this is called as N-type semiconductor. What type semiconductor, children? N-type, negative type semiconductor. So therefore you can say majority charge carriers Majority charge carriers are what? Electrons. Electrons are rich over here. Easily it can be removed out and then it can go to the conduction band. So therefore I am going to modify this. Since it has a tendency to donate the electron, therefore it is called donor impurity. Hence here N-type semiconductor produces an additional energy level. Why additional energy level, you may be wondering here? Because already excess amount of electron is present, therefore you little amount of energy is needed. Very, very little amount of energy is needed for this electron to move towards the conduction band. Therefore this donor level has to be drawn just below it. This is called as donor level. This is donor level has to be drawn just below it, and whose energy is 0.01 electron volt. So, only with the 0.01 electron volt, so you will be able to move this electron, jump to the conduction band. Okay, got it, jump to the conduction band, whereas the valency band filled electrons, valence shell electrons, already it will be there. So, now here what happens, you have to show 10 electron for silicon atom. For silicon it is 4 electrons, and here phosphorus 5 electrons, 1 thermally generated electrons, 1. So, therefore, that is equal to 9 plus 1 is equal to 10 electrons. You have to show here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 is thermally generated electron, equivalently 1 hole you draw here, that is all. So, this is called donor energy level, this is called as N-type energy band diagram. Same way, let us go to the P-type energy level, P-type semiconductor. How do you get P-type semiconductor? Obtained by adding trivalent impurity. So, I am going to add trivalent impurity, so that you can get excess number of holes. So, for example, aluminum you take. Aluminum atom has got only valency 3, it forms a covalent bond with adjacent silicon atom, whereas for the formation of the fourth covalent bond with the neighboring silicon atom, you need 1 electron. So, there is a deficiency of the electron, This deficiency of electron is nothing but hole. So, therefore, 1 aluminum atom seeks 1 electron to form a covalent bond. So, therefore, this kind of impurity, call it as acceptor impurity. It has a tendency to accept the electron. So, therefore, this is called as acceptor. 1 aluminum atom produces 1 hole. So, therefore, n aluminum atom produces n hole. Already existing with the silicon atom, already Ne is equal to NH exists for silicon atom. But now on adding, what are you adding? Trivalent impurity. Now on adding trivalent impurity, you get excess holes are produced. So, therefore, you can say that excess holes is nothing but deficiency of the electron. It needs some energy to accept the electron. So, therefore, where the electron is from the valency band, hence the donor level has to be drawn just above the valency band. Holes are produced. So, therefore, you have to draw a donor energy level, that donor energy level to be drawn just above the valency band. So, this is called donor energy level. This donor level ED is varies from 0.01 to 0.05 EV. So, now silicon has got 4 valency, now trivalent impurity aluminum has got 3, so and only thermally generated is 1. So, therefore, 7 plus 1 8. So, the 8 electrons, 8 holes you have to show here in the valency band. So, I am going to show you in the valency band 1, 2, 3, 4, 5, 6, 7, 8. So, 8 holes I have shown, so only 1 thermally generated electrons here. So, therefore, P-type semiconductor is obtained by adding trivalent impurity. Since holes are rich, therefore, it is called as positive type. So, majority charge carriers are holes. So, hope you understand now energy band diagram for the N-type and P-type. I am going to show you. So, you can have a look at it before getting into that. I have already told you, as the temperature increases, more thermal energy become available to this electron. Some of this electron may break away. That is nothing but semiconductor at greater than 0 Kelvin. The thermal energy effectively ionizes only few atoms in the crystalline lattice and creates a vacancy in the bond. The neighborhood from which the free electrons has come out leaves a vacancy with an effective charge. Hence, electrons and holes are produced. So therefore, he says that Ne is equal to NH is equal to Ni. Now, we are talking about the energy band diagram of N-type and P-type, which I have already showed you, shared you. You can see the same thing. Yeah, N-type semiconductor and P-type semiconductor. So, N-type semiconductor donor level is created, whereas P-type semiconductor acceptor level is created. So, hope you understand till this, children. So, the next video we will just see about the pre-n junction formation. Thank you, children.